In this segment, we're going to talk about finding the Pareto front. Returning to our canonical trade space representation of a top-level benefit versus cost scatter plot, the most salient feature in such a representation is the shape of the cloud of points. The key feature to focus on in such a representation is the boundary of minimum cost and highest benefit. This represents the set of objectives that we most care about. The Pareto front represents the classical best solutions in a trade space. It can be algorithmically determined and contains a set of non-dominated solutions, those that are most efficient across our considered objectives. Typically, in this top-level representation, it's benefit versus cost. Here, we care about minimizing cost and maximizing benefit. There are two key types of designs in our trade space: our Pareto front designs and our dominated designs. Strictly speaking, in this representation, we can always do better than our dominated designs. That is, we can find alternatives that are higher benefit at the same cost, or lower cost at the same benefit. High value tends to be considered to be the top left corner in such representations. Unfortunately, we can never reach our utopia point of zero cost and maximum benefit, as real-world constraints tend to limit what's feasible. The Pareto front represents that most efficient trade-off that is feasible. Consider an example application of trade space exploration for planning a wedding. This was done by one of our grad students a number of years ago as a way to show the benefit of using such an approach for considering a large number of alternatives for a consequential decision. The key decision maker in this case was the fiancé. The different design points included aspects of location. The evaluative model was judgment of how those different locations performed in terms of the value metrics. This student fixated on the Pareto front, and the Pareto front held two different types of designs. One that was located in New Orleans, another in Maryville. The New Orleans designs were the more expensive ones, but higher benefit, whereas the Maryville were the lower benefit and lower cost. This study was done in an afternoon and was an example of a quick and dirty approach to trade space exploration that helped to focus the conversation on two key locations. One surprise was that Colorado Springs was dominated and quickly was removed from consideration. Now, if we're going to fixate on the Pareto front, it's important to recognize that the shape of that Pareto front is determined by our sampling strategy. As you can see, as you add more design points, the Pareto front shape changes. We consider a Pareto front converged if the shape remains the same across multiple levels of sampling. Once we have confidence that the Pareto front is converged, the next step is to ask the question, what are good value designs? Good value designs are determined by investigating designs that lie along the Pareto front. These represent our benefit-cost trade-offs. As an example, consider the ship design trade space. Looking along the Pareto front, we see that there's a trade-off. Small beam designs dominate the low-cost end of the Pareto front, whereas increasing beam eventually changes over to large cargo space arrangements in the higher cost regimes of the trade space. Typically, we take our Pareto set designs and put them in a table for comparison. This tends to be viable as long as the number of alternatives is not too large. And one might care about more than just those designs on the Pareto front. We might do this if we believe there's some location inaccuracy in our trade space. This could be due to uncertainty in our design representation, in our evaluative models, or in our value models. Additionally, we may want to allow for good enough solutions that are near the Pareto front. This might mean that we would allow for some distance from the Pareto front. We call this a fuzzy Pareto set. Fuzzy Pareto set are those designs that lie within some k% distance of the Pareto front. As k goes from 0 to 100, we go from the classic Pareto front to the full trade space. Different decision makers will have different allowance for different fuzziness levels. The fuzzy Pareto number is a metric that represents the distance from the Pareto front for a given design. If the fuzzy Pareto number for a point is 0, it means it lies on the Pareto front. If it's 5, that means it's 5% from the Pareto front. We may also believe that we have incorrect or incomplete objectives considered. As the number of objectives goes to infinity, all designs eventually become Pareto efficient along some objective. Additionally, we may consider that the objectives may change over time. This means the design points that are in the Pareto set today may not be tomorrow and therefore may not be the best solutions over time. We further discuss algorithms for determining the Pareto front and the fuzzy Pareto front in the supplemental materials.